So today we're going to continue our discussion on maximum and minimum values. We're going to talk about more on the second derivative test and also how to find absolute value, absolute maximum and minimum values. So remember that what we decided last time is that for the time being, for relative max and mins, when you have a continuous function, some differentiable functions, so we have tangent planes at every point, those, the local max and local min will appear, let me do it in this color, when the tangent planes are parallel to the xy plane, those are our candidates to have a max or a min. But there are some other points that are fakes. There is what we call a saddle point, where the tangent plane is also parallel to the xy plane, but there is no max or min. It's a saddle point, because there are two directions, and in one it's giving me, it is a local min in one direction, and in another one it's a local max, and that mix signals, it's read as, well, the tangent plane has to be flat, but it is not a local max or a local min. So how do we check what's happening? First of all, we are going to detect where there might be local max and local mins by finding places where the tangent plane is parallel to the xy plane. And that happens when what we call the gradient vector vanishes, or when the gradient vector both coordinates are zeros. Okay? And so let's remember how to do that. So first, how we found some critical points. We did this at the end of last lecture, but this just find what are the derivatives with respect to x. Here is 2x minus 2. The derivative with respect to y is 2y minus 6. And this will be 0, so that the gradient vector vanishes when x is equal to 1 and when y is equal to 3. Okay? So that tells me that there is a unique point when there is a criticality, where there is a critical point, is only one point. So the only critical point is at 1, 3. And we want to decide what kind of critical point that is. We actually saw last time that I completed coordinates, I completed the square in the coordinates to see that this is some sort of paraboloid that is precisely above the point 1, 3 in the plane, and it's 4 units up. So that is going to be a local min, which is also going to be a global minimum. But how do I decide, when functions are much more complicated than this, whether it's a local min or a local max? We use a second derivative test. What we're going to do is, in fact, take, instead of a tangent plane, we already know from calculus 1 and 2, we know about Taylor series. The tangent line is, in fact, the first Taylor polynomial of a function. Then you can do a second degree Taylor polynomial, and third degree, and so on. Similarly, a tangent plane here is going to be a first degree linear approximation. So it's a first degree Taylor polynomial in two variables. You can do the second degree Taylor polynomial, and second degree Taylor polynomial is going to be a quadric surface that matches the behavior of your surface at that point up to degree 2. And then we can compare that with the behavior of quadrics to see, is that a paraboloid, is that a paraboloid, is this a hyperboloid? And we can verify what's happening at that point. And that's what the second derivative test tells you in two variables. So if the function is nice, we haven't talked in this class, unfortunately, we haven't talked about continuity, differentiability. That's something that you will see if you go on to analysis, the dreaded course for all math majors. If you go into analysis, then you'll see what is the definition of differentiability in general. But in any case, if you have a nice function that has a critical point at a, b, then you compute this auxiliary number, this quantity. This is the second, the pure derivatives, the second pure derivative, so with respect to x and then with respect to x, with respect to y squared, multiply them, and then subtract the mixed derivative squared. That, by the way, you can remember it as this determinant of second derivatives, and but just remember that when the function is nice, actually those two derivatives actually coincide, so that's why there is no fyx in this formula. It's because those coincide in this case. And that, by the way, is called Clairaut's theorem, that those two will coincide. But in any case, we compute this auxiliary number in this case, and it gives me a criterion. When this number is negative, let me start there, then it is a saddle point, end of story. It's not a local max or a local min. Now, when d is positive, if the second derivative with respect to x is positive, then there will be a local min. Remember that the second derivative being positive means that the first derivative is increasing, and you can think about the tangent line going like this, so it has to make a local min. And when the second derivative with respect to x is negative, that means that the first derivative is decreasing, and then you can see that it has to be making a local max at that spot. Okay, so this is the way I remember these things. And importantly also is that if this number is 0, the test is inconclusive. Just like in the first variable case, when you were doing a second derivative test and you get that the second derivative is 0, you cannot use the second derivative test and you have to do something else. Okay, so let's put it to use to classify that critical point we found before. So we found before that 1, 3 was critical. And now I have to figure out, using the second derivative test, what kind of critical point I have. So let's figure out, again, what is the first derivative. The first derivatives were 2x minus 2 and 2y minus 6. And then I have the second derivative with respect to x, that's just 2. If I do now a derivative with respect to y, there is no y's there, it's just 0. If I do the first derivative or the second derivative with respect to y, that will be a 2. While if I do the mixed derivative here, I get again 0. Okay? So now I compute my value of d. Remember, it is second derivative, pure times pure minus mixed squared. So that is 2 times 2 minus 0 squared. That is 4, which is positive. And the second derivative with respect to x is 2 is also positive. So that means, first of all, that d being positive means that it's a local max or min. And the second derivative with respect to x being positive, again, means that it has to be a local minimum. So these two things together say that there is a local minimum at 1, 3. We know that because we know it's a paraboloid that opens up, so it has to be a local min. The fourth is bigger than 0. Remember that just tells you that is the first part of the test. That 4 is bigger than 0 is just this condition, but there are two possibilities. And because the second derivative with respect to x was 2, bigger than 0, then it is a local min. If that second derivative was negative, it would have been a local max. Okay, let's do another example. Let's look now at this function. This is not so clear what kind of quadric this is, what kind of quadric surface this is. So let's start working. First of all, I need to find the critical points. So let's start with the gradient vector. So the coordinates of the gradient vector are the derivative with respect to x is 2x plus 4y. With respect to y, I get 4x plus 2y. Right? Check my work because I get my algebra wrong all the time. Okay? So now I want this, I want to know when these two things vanish at the same time. So from the first equation, what I get is that y would be minus 2x divided by 4, so minus x divided by 2, right? And then if I plug in the second equation, I plug in that y, then I'm going to get 4x plus 2 times minus x divided by 2. That is going to be 4x minus x, it's 3x. And that has to be equal to 0, so that tells me that x is 0. Okay? But then because, so now this one and this one together, x is 0, so y has to be 0. So there is, again, just one critical point. And it is the point 0, 0. Okay? But I don't know if it's going to be what kind of critical point that is. So let me now use the second derivative test. Okay, so I have 1 point, and now I have to use the second derivative test. By the way, this is the great reveal of what's happening is that it is a saddle point. This is the graph of the function. So there's going to be a saddle point. Let's see that the math agrees. So I had the first derivative was 2x plus 4y. Then the second derivative with respect to x will be 2. The mixed derivative will be now with respect to y, I get a 4. If I start now with the first derivative with respect to y, which is 4x plus 2y, then I get the second derivative with respect to y will be 4x. Whoa, no, I'm looking at the wrong place. With respect to y is a 2. And the mixed derivative, you can see in check again Clairaut's theorem that with respect to x, I get a 4. And I get the same value for both mixed derivatives. Okay? So then d, by the formula that is at the top, will be 2 times 2 minus 4 squared. So that's 4 minus 16, which is minus 12. That is negative, and that tells me that it is a saddle point. Okay? These second derivatives, they were just constant functions, but they could have been functions of x and y. Okay? And then I would have to plug in at my critical points, several critical points, just to check what the values of those numbers are at the point I'm evaluating. In this case, it just happened that this is just minus 12, so it's minus 12 for any critical point. But it is minus 12 in particular at 0, 0. So 0, 0 is a saddle point, and you can see it right there that it's a saddle. D negative, it's always a saddle point, end of classification. It is not a local max or local min. You can see that there's nothing else to say because there are points here that are higher in value, and there are points here that are lower in value, all nearby. So it's not one of the extreme values of the function. It's just a point where there is some change of growth. Yeah. I was just double checking again, so showing you several times that they coincide. So actually, I did not need to find this one, like you say. I could have stopped and not show it. I'm just doing it just to emphasize the point that they do agree. So either one, if I had done either one, I would have been okay. Yeah. Yeah, as long as the function is nice, but like the functions that you're going to encounter in this class are nice, and these are going to coincide. Those two functions will be the same as I said. If the function is nice, there's a theorem that says that those two mixed derivatives, you get exactly the same function. It's surprising that those are, because like when you take a derivative with respect to x, they seem very different. So it's surprising that they end up in the same place. But if the function is nice, those two actually end up indicating the same slope. What I said is that these functions here, they just, because this was quadratic, these functions ended up just being constants, but they could have been just functions of x and y. And I wish I had an example. I'm not sure I have an example where these are actual functions of x and y, but these could have been functions of x and y. And then to compute this number, you have to plug in at the critical point. In this case, it was 0, 0. So if this was 2 sine x, I would have plugged in at 0, 0. And this was 4 times e to the t. I would have plugged in 0, 0 just to see what the value of those derivative is. So you are evaluating those functions at the point AB, where AB is a critical point. So now that we know how to evaluate where the local max and mins might be, we need to figure out what is the global max and min of a function. So the absolute maximum will be some value at some point of the function that is larger than all the other values of the function in the domain. And an absolute minimum will be a value of the function that is smaller or equal to any other value in any point of the domain. And we have something called the extreme value theorem for functions of two variables, that if your domain is closed and bounded, then there will be a maximum value and there will be a minimum value. So our job is to find them when those domains are closed and bounded. So some bounded region in space, in the plane. So how we are going to do that, we're going to do it in 2 steps. We're going to find the critical points. If you're just trying to find the maximum value and the minimum value, the absolute max and the absolute min, you actually don't need to classify at this point what is happening with those critical points, because I'm just going to, there's this theorem that tells me the critical point will be either at one of those critical points, the largest value and the minimum value, the max value, absolute max, absolute min will be at one of the critical points or somewhere in the boundary. So first I'm going to find all the critical values, evaluate f, and then I'm going to find what is the maximum value on the boundary and what's the minimum value on the boundary of my set, of my domain, and then see which number is the largest and what number is the smallest. So let's do that. So here's an example. I have a function, and I have a region. What kind of a region is that? It's a circle of radius √3, right? Because of 3 here is the radius squared. So the radius is a square root of 3. So I'm going to draw it like this. And my domain is, the boundary is a circle, and it's all the points inside the circle. So it's a filled-in circle. And then I have a function above that, some graph. I don't know what that graph looks like. It's a degree 3 polynomial. I have no idea what that's going to look like. So I want to know what are the possible max and min values for that function in that region. So first, let's look at critical points. So 1, I'm going to look for critical points. So I need to find those where the gradient vanishes. So the derivative with respect to x is y squared. The derivative with respect to y is 2xy. And if these two vanish at the same time, what do I get? Well, I get that either this one tells me that y has to be 0, okay? And then that makes that vanish anyway. If y is 0, 2xy is 0 anyway. So there's actually a lot of critical points. So any point, any x, comma 0 will be critical. Okay? For any x. So what points are those that are critical? Are all the points in the domain where the y coordinate is 0, so it is all of these are critical. That's bad. If I want to classify those critical points, I would have to actually now, I don't know, try to classify infinitely many points. But as I said, you don't have to classify these critical points. I just need to know what is the value on these critical points. So let's evaluate at those critical points. What is the value of the function at any point where y is 0? Well, the function is x times y squared, so the value is 0. Okay? So this is my first value to keep in mind, that so it is 0 in that yellow line in the circle, the function is just 0. And maybe that's the maximum value, maybe that's the minimum value, I don't know. Maybe it's neither. So let's keep that in mind, that I have to compare at the end this with the other ones. So this is what happens at critical points. So I'm done with the critical points. Okay? Now I'm going to switch to the boundary. So now at the boundary, I have just the circle, not the filled-in circle. And I want to know what is happening at the function in this boundary. So I want this function on x squared plus y squared equals 3. Any suggestions on how to figure out what is happening with this function at those values? How can I get a hold of what the values are in that circle? Yes, yes. So in many cases, I'm doing everything as, okay, let's do it as 2 variable functions and work with 2 variable functions. But there are many cases where I can actually do something to make my problem be a function of 1 variable. And this is one of them, where here I can solve for y. Y squared is 3 minus x squared. And that tells me that this function is actually a function of just x on that circle. It's x times 3 minus x squared. Okay? And now this is just a function of 1 variable. And I can figure out where the max and the min are for that function. By the way, here the function x and y are between minus the square root of 3 and the square root of 3. So I'm looking at this function x times 3 minus x squared between these bounds. And I want to know what is the maximum, the minimum value in there. And that's going to give me what are the values on the circle. So to figure that out, I can do critical points on this function. So as a function of 1 variable, this is, by the way, 3x minus x cubed. As a function of 1 variable, this is, the derivative is 3 minus 3x squared. And the critical points for that function will be when this is 0, and that tells me that x squared is plus or minus 1. And when x squared is plus or minus 1, I can use this formula to tell me that y has to be plus or minus the square root of 2. I'm sorry, this is x is plus or minus 1, right? X squared is 1, so therefore x is plus or minus 1. And when x is plus or minus 1, plug in here, and I get that y is plus or minus the square root of 2. And again, I don't have to classify, is this a local min, is this a local max for this graph of one variable? These are, again, some critical points, and I have to check what happens at the boundary and what happens at these points. So let's see, at the boundary, that's when x is plus or minus the square root of 3, f of x is, plug in the square root of 3 here, the square root of 3 minus that square root of 3 squared will give me 0. So the value is 0 at those points. Okay, so that tells me that here the value is 0, here the value is 0. And then I need to figure out what is the value at the other critical points. So at the critical points, those are when x is plus or minus 1 and y is plus or minus the square root of 2, f of xy is what? X times y squared. Y squared, because y is the square root of 2, is just 2. This will be plus or minus 2. So that is large. So when x is 1 and the square root of 2 and y is the square root of 2, so at x equals 1 and here y is the square root of 2, so at 1 comma the square root of 2, the value is 2, while at minus 1 and the square root of 2, at this point minus 1 and square root of 2, the value is minus 2 for the function. So these are the max and the min. So the max is 2, the min is minus 2, and they happen at that point and at this point. They also happen there, actually, yes, because it is, the y is plus or minus, so you're totally right that if you go here to minus the square root of 2, there is another point, 1 minus the square root of 2, where the value is also 2. So here's another point where there's a maximum, and it also happens here at the point minus 1 minus the square root of 2, the value there is minus 2, so that is also a critical point. So it happens in 4 points. And remember that the other values that we had were 0 in the entire x line, so that is in between minus 2 and 2, so those are not extreme. So the extreme values are here, in those 2 points here, in the frontier, so in the border of the domain, at those 2 points the value is 2, and in those 2 points the value is minus 2. So the boundary here, we also have to figure out what is the absolute max and min of a function in an interval. So when you were trying to find in calculus 1, I think, the absolute max and min of a function in an interval, you have to find the critical points and also evaluate at the borders, so at the endpoints of the interval. In this case, this function at the endpoints is 0, so it doesn't matter. Okay?
How did you find it was 0?
I plugged in. So the boundary is when x is plus or minus the square root of 3. Plug in the function, plug in the value in here, and what you get is that x is the square root of 3, is 3 minus the square root of 3 gives me 0. Okay? Because it has to be a point on the circle, it has to satisfy this, has to satisfy this. So in any case, the function at those points vanishes. Other questions? Let me just repeat that there are 2 steps in the process. I find the critical points, like 2 variable critical points in the interior of my graph, of my domain, using the 2 variable criterion. So find where is it that the gradient is vanishing. And that gave me the points x comma 0, so all of those are critical, but the value there is just 0. And then what I did is restrict to the border of my region, which is just when x squared plus y squared is equal to 3. And then I'm going to look at this function exactly in this region, so I can solve for one of the two variables and make it a one variable function, and then figure out what is the largest value of that function in that interval.